In today's video, we're going to look at another method of evaluating determinants known as cofactor expansion. So in this video, we first have to define a few terms needed for the method, and then we will delve into the actual method itself. So this method reduces the problem to the evaluation of matrices of a lower order. So for example, if we're looking at 5 by 5, this method will reduce it to evaluating determinants of 4 by 4s, which we can then also reduce each 4 by 4 into determinants of 3 by 3. First, we need a couple of terms. So let A be a n by n matrix. Let Mij be the n minus 1 by n minus 1 submatrix of A, which is obtained by deleting the ith row and jth column of A. The determinant of this Mij matrix is called the minor of the ij entry. The cofactor aij of the ij entry is then -1 to the I plus j times the determinant of Mij. So what we'll do now is go ahead and find all the cofactors of this matrix here. All right, so there's going to be a total of 9 of them, right? So let's start with A11. Right, so I is 1, j is 1, so we have -1 to the 1 plus 1 times the determinant 5, 6, 1, 2. Right, so what we did was we took out the first row, the first column. Right, so in a sense, what we did, since we're looking for the cofactor of this entry right here, right, we cancel out row 1, column 1. We cancel out the row and column it is located in. And then we take the determinant of the matrix that remains. And of course, we know how to take a 2 by 2 determinant. So we get 5 times 2 is 10, minus 6 is 4, right? And -1 to the 1 plus 1 is just +1. So we're left with 4. All right, let's look at the 1, 2 cofactor. And what we want to do is something very similar. Right now we're looking at the 1, 2 entry. So again, cross out the row it's located in, as well as the column. Take the determinant of the matrix that's left, multiply it by -1 to the 1 plus 2. At this cert, we get -8 minus 42, which is 34. Now for A13, again, this is now the cofactor of the 1, 3 entry, so cross out its row, its column. We get -1 to the 1 plus 3 times the determinant of 4, 5, 7, 1. Right, -1 to the 1 plus 3 is +1, so we get 4 minus 35, and that cofactor is -31. Right, and we want to do the same thing now for the next 2 rows. Right, so A21, -1 to the 2 plus 1 times the determinant of -1, 2, then 1, 2. Right, so -2 minus 2, we get +4. A22 is negative 1 to the 2 plus 2 times the determinant 3, 2, 7, 2. We'll have 6 minus 14, which is negative 8. Right, and then finally, A2, 3, negative 1 to the 2 plus 3 times the determinant of 3, negative 1, 7, 1. So negative 3 plus 7, we get negative 10. Final row, A3, 1, negative 1 to the 3 plus 1 times the determinant negative 1, 2, 5, 6. Right, so this is negative 6 minus 10. We get negative 16. A3, 2, negative 1 to the 3 plus 2. Now times the determinant 3, 2, 4, 6. We get negative 18 minus 8. So negative 10. And finally, A3, 3, negative 1 to the 3 plus 3 times the determinant 3, negative 1, 4, 5. Right, so we get 15 minus negative 4 is 19. And so there is all 9 cofactors of this 3 by 3 matrix. Let's now look at the actual method. So we let A be a n by n matrix. Then the determinant of A is AI1 times big AI1 plus AI2 times big AI2 plus so on and so forth plus AIN times big AIN. In other words, it is the I1 entry times the I1 cofactor plus the I2 entry times the I2 cofactor plus so on and so forth plus the IN entry times the IN cofactor. And this is known as the expansion along the ith column. Ith row, rather, I'm sorry. That should be ith row. We also have determinant of A being A1j times big A1j plus A2j plus big A2j, so on and so forth. In other words, the 1j entry times the 1j cofactor plus the 2j entry times the 2j cofactor plus so on and so forth plus the nj entry times the nj cofactor. And this is the expansion along the jth column. Right. So it doesn't matter what row or what column. When you have a matrix, choose any row or any column and do cofactor expansion along that. Doesn't matter how you pick it, you'll get the same determinant. All right, for the proof, we first notice that equation 2 here follows from equation 1 by theorem 1 from lesson 2.1. Now, for this proof, we will only consider the case of n equals 3. So we're only going to prove this for a 3 by 3 determinant. Now recall that the determinant of A, by definition, is this. This term here should have been 3, 1. Now what we're going to do is we're going to algebraically manipulate this. So take a look at A11. So factor out A11 from its terms. We get A22 times A33 minus A23 times A32. Factor out a negative A12. We're left with A21 times A33 minus A23 times A31. Then we can factor out an A13 and be left with A21 times A32 minus A22 times A31. But this equals A11 times this determinant minus A12 times this determinant plus A13 times this determinant. Right? But if you look at this first determinant, isn't that the cofactor, the 1, 1 cofactor, right? Then we have plus A12 times the 1, 2 cofactor plus A13 times the 1, 3 cofactor. Right, so notice that this last expression, the one we just wrote, is the expansion along the first row. Similar manipulations will yield expansions along the other rows. And again, remember that the columns follow directly from the row expansion. So you're encouraged to try to do similar manipulations to get the other 2 rows. That will not be done in this video, so this proof is complete. Now to actually apply it. Now, since it does not matter which row or column we expand across, let's pick the most convenient row or column. Well, if we look here, row 3 has 2 zeros, column 2 has 2 zeros. Both of those are equally convenient. So let's just take expansion along row 3. Right, so this determinant. We get the 3, 1 entry. So negative 1 to the 3 plus 1 times 3. Now times the determinant of what remains, 2, negative 3, 4, 2, 1, 3, 0, negative 2, 3. The 3, 2 entry and the 3, 3 entry are both going to wind up being 0, right? So we don't need to worry about that. We now look at the 3, 4 entry. That's going to be negative, so it becomes negative, negative 3, which is positive 3. Then times the determinant of 1, 2, negative 3, negative 4, 2, 1, and then 2, 0, negative 2. Now we could try and do cofactor expansion on these two matrices. However, we do have a technique already for 3 by 3 determinants, so let's go ahead and use that technique. But we're going to 2 times 1 times 3 is 6, plus 0, plus 4 times 2 is 8, times negative 2 is negative 16. Then 2 times 3 is 6, minus 2 is negative 12, so minus negative 12. Negative 3 times 2 is negative 6, times 3 is negative 18, minus negative 18, and then minus 0. Using the same technique, we will get negative 4, plus 4, minus 16, plus 12. Didn't write out the zeros here. So we get 3 times 20 plus 3 times negative 4, which is 60 minus 12, which is a determinant of 48. And that concludes the video on cofactor expansion. So the key with cofactor expansion, as we saw, is to choose the row or column that has the most number of zeros, as this will reduce the problem into its simplest form. However, it doesn't matter, right? You can choose any row or any column to expand across. In the next video in the series, we'll finish up our study of determinants by looking at 2 applications. The first application has to do with using determinants to find the inverse of a matrix. The second application is using determinants to solve a linear system. As always, thank you for watching. I hope you enjoyed, and I will see you all in the next video.